In the following lecture, we will explore the summation property of statistics. Addition is a very common operation in statistics. Shortcut notation is used because of the frequent use of summation. In statistical operations, the Greek capital symbol sigma is used as the summation sign. Here's an example. Sigma x means the summation of x. Suppose we want to add the series x sub 1, x sub 2, x sub 3, x sub 4, and so on until we come to x sub n. The shorthand notation for the summation of this series is sigma, or the sum of x sub I. X sub I represents the entire series to be added. Starting with x sub 1 and ending with x sub n. X sub n is simply the last variable to be summed. Stated all together, we want to find the sum of x sub I where I ranges from 1 to n. Let's review the summation notation in detail. This notation is read as the sum of x sub I where I ranges from 1 to n. The I equals 1 in the blue box indicates that the first value to be summed is x sub I. The n above the sigma stands for the last value in the series x sub I. While this example may seem confusing at first, simply look closer to see how the observation numbers match up with the data and the data values. Each observation number has a corresponding x value, as well as a data value. See that the data value for x sub 1 is 4, x sub 2 is 7, x sub 3 is 9, and so on. This summation property indicates that the sum of x sub I plus y sub I is equal to the sum of x sub I plus the sum of y sub I individually. To verify this property, simply see that the left half of the property means to add the first x and the first y, the second x and the second y, and so on to arrive at a number. This number will be equal to the right half of the equation, where we add up all the x's and all the y's separately before adding them together. By inserting the data values in the place of the x's and y's, one can deduce the equation at the bottom of the screen. Feel free to pause the slideshow to verify that both sides of the equation at the bottom of the screen add up to 37. This is an application of the summation property for subtraction. This property states that the sum of each x sub I minus y sub I pair is equal to the sum of x sub I minus the sum of y sub I. By substituting the data values for x sub 1 and y sub 1 variables, one can begin to create the equation at the bottom of the slide. Continue through the variables to finish the equation and then solve it. Both sides equal 7. Once again, feel free to pause the presentation in order to review the material on this slide. In properties 2 and 3, c is a constant. A constant is a number that doesn't change. Property 2 indicates that the sum of the series from 1 to n multiplied by c is equal to n times c. For example, the sum of 3, where I ranges from 1 to 4, equals 3 plus 3 plus 3 plus 3 equals 12. This is equivalent to 4 times 3 equals 12. Property 3 is a derivative of property 1 and property 2. This property indicates that the sum of x sub I plus c is equal to the sum of x sub I plus n times c. This equation is read as the sum of c times x sub I is equal to c times the sum of x sub I. If this notation seems confusing, try looking a little closer. Break down the equation into parts. Every time there is a sigma, the notation will involve the addition of a variable. Then, just look for any other function that may be present. In this case, multiplication of the summed variables times a constant. Read this as you would any other table. But for now, don't get caught up in the numbers of the body of the table. The replicates are rows, and the treatments are columns. To indicate the manner in which summations are to be done, we need to use a system of double subscripts. Once again, the replicates are rows, and the columns are treatments. The letters I and J are commonly used as subscripts with double summation. The general notation for any data point would be x sub I, comma, j. To help remember what I and j stand for, think of I as in I write from left to right, and try to remember j as in J for jail bars. Follow the table. The value at row 1, column B, read as x sub 1, comma 2, represents the value 752. The value at row 5, column E, read as x sub 5, comma 5, represents the value 749. If we sum all the points in the data table, the notation for this double sum is written as the sum of x sub I, comma j, starting with j, equals 1 to c, starting with I equals 1 to r. Assume that the previous experiment was conducted in different locations. The locations will be denoted by the subscript k. In this slide, we will examine three-way classification. For example, k will represent the location. Now let's take a closer look at the content of the tables. Both tables represent different locations, and accordingly, the data within the tables differ from each other. The I still represents the rows, and j the columns. The only difference is the experiment was carried out in two different locations with two different sets of animals. The locations can be anywhere as long as there is a documented physical distance between the experiments. Groups of observations are conveniently described by a single number. Central values, most frequent values, and middle values are most commonly used because they represent a typical value in a group of observations. Measures of central tendency are the representative of the typical or representative value in a group of observations. The most common measures of central tendency are arithmetic mean, median, and mode. Mid-range, geometric mean, harmonic mean, and weighted mean are less common measures of central tendency. Arithmetic mean is the most common way to evaluate central tendency. Arithmetic mean is calculated by adding up the observations and dividing by the number of observations. This technique is familiar because it is the same as taking the average of a group of observations. The designation for arithmetic mean is x bar and is usually referred to simply as the mean or the average. This notation is read as the sum of x sub I divided by n. If, for example, there were a total of 5 observations, then n would equal 5. Review this set of observations. X sub 1 has a value of 4, x sub 2 a value of 5, and so on. To calculate the mean, simply add up or sum the different observations and then divide by n. The sum of x sub i's is 4 plus 5 plus 7 plus 9 plus 2, which equals 27. Now that we have summed the values, simply divide by n. In this case, n is 5. 27 divided by 5 results in an arithmetic mean of 5.4. The median of a set of observations is simply the middle number when arranged by size. These data values are in no particular order. In order to find the median, they must be placed in order of increasing or decreasing size. Once the observations are ordered by size, it is simple to determine the median. The median is always the number in the middle position. When the number of observations is an odd number, there will always be one distinct median. In this case, the middle number in the ordered observations is 5. In many cases, there are an even number of observations from which the median must be derived. In this example, there are 6 observations. These observations are already in increasing order. Since there are an even number, there will be two observations in the middle. The two middle observations are 4 and 5. In this case, the average of the two middle observations will represent the median. Add 4 plus 5 to get 9, and divide by 2 to get a median of 4.5. The mode is the most frequently occurring number in a group of observations. It helps to arrange the values in increasing order to be able to see duplicate numbers more clearly. In this case, the only number present more than once is 2. There is not always a mode in every data set. For this series, there is no mode. In some cases, there are more than one mode present in a data series. Here, we see that there are two modes. The two modes are 2 and 4. This data is referred to as bimodal.